should work. So, how it is organized? This first session, we are going to have a kind of scientific introduction to one of the main topic of interest of the ACME project. Okay, that is multi-messenger science, and in particular in the field of gamma ray burst as transient multi-messenger source, astrophysical source. So I will provide a rather generic observational review of gamma ray burst properties, focusing of them being multi-messenger sources. Then Lara will provide a more theoretical review, mostly focused on the high energy emission. That is also the topic of the data analysis part of this workshop. And we will see how, for example, the instruments, the satellite Swift and XMM, can play a role in the study of this. There will be some time, so we organize well ourselves, for some question after the end of the talk. But then, as you have noticed from the program, there will be almost half an hour open discussion session on what we discussed with the panel here, together with Giancarlo and Maria Grazia. So there will be plenty of time, hopefully, for discussion and so on. How many of you are familiar with gamma ray burst or are doing gamma ray burst in their own research? Okay, so a generic audience. So this was the goal. Okay, so gamma ray bursts are astrophysical events. They are brief, unpredictable, very intense flashes of gamma ray radiation, exactly as the name suggests. So this is an image from the LAT instrument on board of the Fermi satellite, right before and during the onset of a GRB. So this is a kind of image of the gamma ray sky, as it is without and with the gamma ray burst ongoing. And as you can see, a single gamma ray burst can be brighter than the entire brightness of the gamma ray sky. And they have a relatively short duration, but as we will see, there will be probably not that time. It depends, but the time scale can go down to fraction of seconds, down to milliseconds, for the duration of the gamma ray activity. I mean, up to seconds, tens of seconds, hundreds of seconds, and now we are realizing even thousands of seconds. They can let the so-called ultra long gamma ray burst. The bulk of their emission is in this energy frequency range. So we are speaking about hard X-rays, gamma rays. And so the duration we told, and these are the typical flux influences as measured when gamma ray bursts occur, as measured by the high energy satellites. Gamma ray bursts are cosmological. So this is the first important information. So they occur in other galaxies at cosmological distances. So if you are curious, you can go and read the historical reviews. There was a lot of debate. Gamma ray bursts have been discovered in the 60s. And of course, as long as you can send high energy satellites in space, you can detect gamma ray bursts, and this is what happened indeed. And there was a lot of debate if they were galactic sources or cosmological sources. One of the main problems was because once you measure the flux and the fluence, if you put them at cosmological distances, then the energy release is huge. That's why there was also this debate. It is possible to release so much energy in just a few seconds or fraction of seconds. So the first hint of the cosmological nature was here. You can see the distribution of gamma ray bursts as observed by the BATSI instrument. So this was end of the 90s. And so they are isotropical, but the final proof was when it was possible to spot their afterglow, and then we will see what they are, and to precisely localize them and to see that they are occur indeed in galaxies, and then to measure their redshift and prove that indeed they are cosmological. So if you put the typical, let's say for a gamma ray burst, let's say that the peak of the redshift distribution is at around 2 and something redshift. So the typical fluence, you end up with an assuming isotropic emission with an energy release of the order of 10 to the 53 amps, so really, really energetic. Okay, so this is a very famous plot. People working gamma ray burst, a plot now is being discussed a lot. And so the classification. So let's start from the best. So if you take the durations of all these gamma ray bursts, so you take the gamma ray light curve, you measure the duration of the gamma ray activity, then it's the T90, but these are the technical details. How much it lasts, the gamma ray duration. So you call it the T90, the so-called T90. You take all the duration for all these thousands of GRBs, and you discover that the duration distribution of the prompt emission, gamma ray emission, is bimodal. So there seems to be two main classes, the short duration and the long duration gamma ray burst, and with a kind of separation at around 2 seconds. So for decades, and we still use it because it's very useful, we say, okay, if just from the satellite prompt emission detection and duration, if the gamma ray emission is less than 2 seconds, then it's a short GRB. If it is, someone wants to. Grazie mille. Thank you, Lara. Is a short duration, otherwise a long duration gamma ray burst. Okay, two classes. And I anticipate that this idea of two classes puts forward the idea that there were possibly two class of progenitors for these events. Okay, another point is that typically you see here duration and hardness ratio. The short duration GRBs on average have harder spectra. So the peak energy of their gamma ray spectrum is more towards higher energy, more or less. So this is the standard model. The idea is that we have two classes of progenitor, given that we have two classes of duration and hardness for the prompt emission. For the long gamma ray burst, the idea is that the progenitor is the collapse of a massive star, so kind of a collapse supernova. For short gamma ray burst, the idea is that the progenitor is the merging, the coalescence of binary compact objects. So, for example, a binary system made by two neutron stars, or a binary system made by a neutron star and a stellar mass black hole. Whatever is your progenitor, you end up with the formation of a compact object, or either from the collapse or from the merging, you end up with the creation of a compact object that, according to the most popular models, is a black hole, but there are also models that foresee that can be a newly born, highly magnetized, highly spinning, highly unstable, highly whatever neutron star. Okay, and then for some reason, there you have the conditions for the onset of a jet, of a collimated emission, and then you have this jet of expanding material, where you have these shells, and the collision between these shells gives rise, these internal shocks gives rise to the prompt emission. The idea is that you can have multi-spike light curves, and every spike is a collision, internal shock of these shells, and then all the material, the jet expands, and at some points reaches the interstellar medium that is there. And this external shock gives rise to the so-called afterglow emission. So, according to this model, you expect to have, because of whatever is the progenitor, you have the formation of the central engine, the onset of a jet, and this gives rise to the observed prompt emission. Then, later time, you expect the onset of the afterglow emission that has longer time scales. We count in seconds the duration of the prompt emission, while the afterglow, according to the model and then also to the observation, because these are real actors, is expected to emit over the entire spectrum, or wavelengths, or frequencies, and to have a relatively fast decay, like a power law decay, and according to the intensity and so on, it can be observable for days, weeks, months, and so on. Okay, this is the idea. One of the two missions we are going to play with is Swift, and the team will tell you a lot about the satellite. Just to give you the idea, the main idea behind the Swift mission, more than 20 years ago, was to have a multi-frequency satellite, multi-frequency observatory, able to quickly repoint. This is the main idea. So you have a wide field of view hard X-ray or gamma ray telescope, this BAT, and if within the field of view there is a gamma ray burst, then the spacecraft can swiftly repoint everywhere in the sky. Say typical repointing time is 1 minute, 100 seconds, so that the GRB location can fall within the narrow field instruments that are a soft X-ray telescope, XRT, and ultraviolet and optical telescope, UVOT. They have a smaller field of view, but if you can move quickly, you put the GRB position within your field of view, and you can localize it better, because as long as you go towards lower energies, so from gamma rays to X-rays to optical, it is easier to focalize the photons, and so you can obtain precise positions. So with this machine, the idea was within 1 or 2 minutes, we will always obtain precise positions, because with gamma rays, the positions typically are on the order of square degrees of a few arc seconds, so that we can localize the GRB. And thanks to this, it was possible to study, to associate those galaxies, to measure direction. This is how it works, but this is what is the point? We were at this situation before Swift, because this was the situation of the Bepos axial. We had let's say the prompt emission localized by some gamma ray satellites, and then before Bepos there was nothing. With the Bepos satellite, it was the first satellite able to repoint to narrow field instruments, and the repointing time was of 8–10 hours. And then, thanks to this, it was possible to discover the afterglow emission of the GRB that was foreseen by the theories. But if you are not fast enough to point, if you cannot precisely localize, you cannot detect it. And so there was a kind of observational gap due to the time of Bepos to repoint. And then it was discovered that the afterglow were there, decaying as predicted, as a power law, let's say. With Swift, everybody was thinking, okay, this is how they should behave, the afterglow of GRBs in the gap we have. Then Swift arrived, covered this gap, and we discovered that things were a bit more complicated. They were not just as smoothly decaying as expected. And so there were the discoveries of flares, plateaus, and so on. I will not spend time to this, but just the idea that the central engine can be active as longer as one can imagine, and that things can be much more complicated than initially thought. And now we have thousands of these lights. One of the great things of Swift, and you have the same telescope observing all of these, so you have a very homogeneous sample. So you can play, the archive is really browsable, you can play, there are a lot of tools they will show us, and so we discover early flares, late flares, and a lot of stuff to make all the theory people very happy. Anyway, so the progenitors, okay, 2 classes, long soft, the collapser, the supernova, short hard, the merger, the compact binary merger. Just to give you an idea, how do we know that long-gamma reverse are originated by massive supernovae? Time, flux. Imagine this is the optical. This is the optical afterglow of a GRB, as you would expect it. So a decay, maybe some flare, but a power law decay. If a supernova originates the GRB, I don't know how many people is working in supernova here, but typically supernovae has a rise in time scales of the orders of days, weeks. So if a supernova occurred there, and then you have the jet and so on, but the supernova is going, doing this stuff in the optical, and reaching a peak within a couple of weeks. So if a supernova is there in the optical, you should observe the GRB afterglow because of the jet interacting with the medium and the supernova expanding, reaching the peak here. So you should observe something like this in the optical. And this is exactly what we observe. A GRB afterglow decaying, some variability, and then at some point, after 10, 15 days, the peak of the associated supernova. You take a spectrum here, and you see the typical spectrum of the supernova. Optical broad lines, high velocity expansion. This is fantastic, the perfect smoking gun. Okay. For the shot, it's much more complicated because you have the merging of now it's the time to see if I go longer shots. The coalescence of two compact objects, so neutron star, or neutron star black hole. First, while they are merging, so losing orbit, they are expected to emit gravitational waves. So this is one of the possible smoking guns for this kind of progenitor. And then there are a lot of other stuff, because another critical parameter is the merging time that strongly depends the fourth power, the initial separation of the system, because this is a system that can be survived to two supernova explosions, for example, or can be a system that has been formed through dynamical capture, for example, in a globular cluster, where you have a lot of stuff, and then you have the formation of it. So the primordial binaries are those which were born like binaries, surviving two supernova explosions, but this can provide kick velocities. So, for example, you expect them before the merging time to are there escaping from the Eros galaxy because of these two natal kicks, for example. So also the position within the Eros galaxy can be an indication of the kind of progenitor. You would expect, for example, an offset with respect to the center of the Eros galaxy. You can expect them to happen in a very low density environment because they moved from the star forming region where the system was born. Or you can have the dynamical capture. This is another possibility. Then you would expect not to have them on the galactic plane of the Eros galaxy, but more likely in the halo, if it is a situation like our Milky Way or the globular cluster. So these are indirect evidences that are for which people search for in order to understand if this progenitor scenario is believable or not. This empty slide reminds me that I have to switch to another set of slides, but it's easy because 1 and 2. That is fantastic. Okay, so sorry for that. Okay, so okay, the layout changed, but the story is the same. So. Like we saw that for long GRBs, the progenitor is very easy to spot. You look for the supernova, if you see it in the optical, then there is no doubt of which the progenitor was. For the compact binary progenitor, it's more complicated. What do we expect? We expect the diversity in the delay times. It depends on the initial binary separation. So we would expect to have them in every kind of host galaxy. Long-gamma bursts are highly related to star formation because of the supernova progenitor. So you expect them in highly star-forming galaxies. And this is indeed what is observed. You never find a long-gamma burst originated by a supernova in an elliptical galaxy, for example. But here, you can expect that these projectors are associated to both young population or a whole population. Everything depends on the merging time and of the initial binary separation. So you can expect them in every kind of host galaxy, early type, late type. Then you would expect the possible offset because of the natal kick. You would expect to have no associated supernova. This is true also for the collapsar. There can be a remnant, unless the remnant can be different according to the projector, because if you have a neutron star and a black hole, the remnant is a black hole for sure. If you have the merging of two neutron stars, the remnant is more likely a black hole, but it can even be a massive, unstable neutron star and magnetar, for example. You expect in all the situations, you should expect collimated geometry because of the jet emission I told you before. You would expect an association with the kilonova, and now we will see what is the kilonova, and you would expect the emission of gravitational waves for this progeny. So the first indirect evidence is confirmed. We have a great statistic of host galaxy in which short duration gamma ray bursts occurred, and we saw them occurring in both early type elliptical galaxies and in the spiral hybrid star forming galaxies. And we also see situations where there is no host galaxy. You go as deep as possible with HFT, whatever you want, you see no host galaxy at the afterglow position. So maybe this is a hint for a high offset with respect to another galaxy, so kick it out. This is a bit more complicated, but there are studying distribution of the light, the position of the afterglow within the host galaxy. We saw evidence for offset higher with respect to long gamma ray bursts. No associated supernova. These are examples of light curves of short gamma ray bursts, where this is what if a supernova would be there, the expected flux measure. And this is what is measured instead, so the flat host galaxy, or limits that can exclude any bright supernova associated, bright or faint supernova associated to short gamma ray bursts. The story of the remnant I will skip. I just leave you as an interesting stuff that a very interesting that then we can discuss later. It's very difficult to understand which kind of remnant is there. So it's not that easy. For example, for a magnetar, you can hope to detect some pulsations, but if it's cosmologically, it's a bit complicated. An interesting thing is that if you can detect gravitational waves from a measure like this, you can expect some residual gravitational wave emission, steady emission after the ring down, if a magnetar is still there, while you expect nothing if a black hole formed after the ring down. This is something that can be interesting also for the next generation interferometers. The collimated emission, I just tell you a thing that I haven't mentioned before. I showed you that the afterglow light curves at all wavelengths, X-rays, optical, whatever, they can be let's say, described, not modeled, by a single power law decay, or a power law decay we superpose some variability, flares, and whatever. But another important thing is that, according to the model, because of the collimated emission, because you have a jet, a relativistic jet expanding, so also for the Doppler boosting effect, you would expect that at some point the jet angle reaches what is the geometrical aperture, so it cannot expand anymore. At the very beginning, it's highly collimated because of the Doppler boosting. And it expands. At some point, it does not expand anymore because you have a kind of physical initial aperture you are confined with. And so, at some point, you are expected at late time to see a achromatic, so same at all frequencies, sudden decrease of the flux you observe. So you see a decay, and then you see a steeper decay at some point. And this is the so-called jet break. This is indeed observed in afterglow light curves, and according to the model, you would expect that the steepening happens at the same time at all wavelengths, X-ray, optical, radio, near infrared, and so on. And this is the what is expected in case of a collimated emission. It is indeed observed, so the emission is collimated. And in this framework, having a big glasses like XMM-Newton, for example, it is very useful because a telescope like XRT do its best for at the beginning when the afterglow is very bright, but then it depends because they are not standard candles. But after 1 week, 2 weeks, and so on, 1 month, then typically the afterglow, in particular for the short, are too faint for record the effective aperture XRT. Then you go there with XMM or Chandra, and you can still detect at late times, and you can check if the observed emission is on the extrapolation of the initial decay, or if you can witness a steepening. Indeed, the majority of jet breaks is in the X-rays has been detected thanks to XMM-Newton or Chandra. And thanks to this, you can, because there are relations, physical relations, we can compute the opening angle that is over a few degrees, as you can see. Then the kilonova association, I will skip this because I will be back later. And then the gravitational waves, because if the progenitor is like this one, you would expect the gravitational waves emission. So let's go on these last 3 evidences for the compact binary merger progenitor. Let's start from gravitational waves. So if you have this kind of progenitor, neutron star, or neutron star black hole, which kind of electromagnetic counterpart would you expect? So we discussed it so far. I hope I convinced you that you would expect a gamma ray burst. We would expect the prompt emission and the afterglow emission. But the gravitational waves are emitted isotropically. So it may well happen that you have this merging, the emission of gravitational waves. Maybe the GRB was there, but you are not sure if the jet was pointing towards you or not. If the jet is pointing towards you, or slightly towards you, you are expected to detect the prompt emission. What if the jet missed you? Because a few degrees of aperture may well happen that you're missing it. Those detected by the satellites, we of course detect because these are the population that is pointing to us. So if we discuss about the afterglow, it depends if we are on axis or off axis. If we are on axis, we see exactly what I showed you so far. So since very early times, you see an afterglow decaying as a power law that may be steepens at some point because of the jet break. If you are off axis, you are going to miss all this initial part. And you are going to see a late time rising afterglow that at some point, let's say, reaches the flux that would have been observed if on axis, then continue the decay. This is the 2 different scenarios that you are expected to witness according to the theory. The big difference being on or off axis. But there is also a predicted isotropic electromagnetic emission for this kind of progenitors. That is the so-called kilonova, also known as macronova, mini supernova. So the idea is that this is so far we are speaking about non-thermal emission. All what I said about the prompt, the afterglow emission of GRBs is non-thermal emission. Kilonova is a thermal transient. Is a thermal transient. That is what happens basically. You have you need at least 1 neutron star. The neutron star is or are disrupted, okay, right before the merging. You have a lot of free neutrons around there, and so you have an ideal situation for the recombination of these neutrons through the process so-called for nuclear physics of rapid capture. So the so-called air process. This is a way, the preferred way for the formation of heavy elements heavier than iron. Okay, and this is a situation where, according to models, you should have the perfect conditions for this air process to occur. So you have the formation of these heavy elements, whose radioactive decay, because they are stable, the decay is powering the thermal emission that is observed, and that is called kilonova because if you do the computation, it is expected to be as bright as 1,000 novae, so 10 to the 42 per second luminosity, more or less. And so you expect a kind of thermal transient peaking in the optical or near infrared, rising on a time scales of hours, few days, depending on the opacity of the heavy elements that has been put. And very rule of thumb, if you are very rich of heavy elements, you will have, so the opacity is higher, you will have the peak time scale of the order of a week, and more in the near infrared. If you have lower opacities, you would expect the kilonova light curve to peak on the time scale of a day, more in the optical rather than in the. So we speak about the blue and the red kilonova. Ok, ho parlato una mezz'ora quindi. Grazie. So this is the last part of my talk. So I hope I gave you a kind of an idea of how observational gamma ray bursts to behave, the two classes, the two progenitors, and their promising, they're being a promising sources of multi-messenger sciences. You know that since 2015, we have the second generation in gravitational wave interferometers, LIGO and Virgo. You know that 10 years ago, they detected the first direct detection of gravitational waves from a binary black hole, and this gave also right to they will award the light collaboration of a Nobel Prize. This was a binary black hole. The two black holes were on the order of 20, 30 solar masses. Okay, there was the search for electromagnetic counterparts, but no electromagnetic counterpart was found. While in the second run in 2017, we had the first gravitational wave multi-messenger event. It was the famous GW 170817, so 17 August 2017, that has been associated, as expected, right, to a short duration gamma ray burst, 170817. And to this also it was found associated an optical thermal transient whose observational properties were fully compatible with the models of the kilonova, exactly as I told you before. And this gravitational wave event from the gravitational wave data analysis was originated by the merging of two neutron stars at 40 megaparsec from our source. Okay, so we had the gravitational waves, then the short gamma ray burst right after, within 2 seconds later, and then by scanning the gamma ray burst has been observed by the all sky satellites, like they were Fermi and Intec. Then we started the scan of the sky area, sky map from the gravitational waves, and it was possible to find a thermal transient, a transient here in this galaxy at 40 megaparsec. And this happened less than about 10, 12 hours after the gravitational wave T0. And then days after, we had the detection of the non-thermal transient, the GRB afterglow, detected in the X-rays first by Chandra, and in the radio first by the So the scenario was exactly this. I can skip. Okay. So this is the scenario for the gamma ray burst and the gravitational wave. We had a sky map, scanned it. We found the kilonova. See, a new transient in this galaxy. And this is how it behaves. You see, the light curve in the optical, in the real infrared, peaking a bit late in the near infrared rather than in the optical. This is the spectral sequence. You see, it starts as a black body, peaking in the blue optical spectrum, and then the peaks shifted towards the near infrared. So something that is expanding and getting colder. And this is the non-thermal emission. So at the very beginning, Swift was pointing, for example, and found no afterglow at all. Then after 9 days, do you remember the off-axis situation? An X-ray afterglow popped out, detected by Chandra, a radio afterglow, again non-thermal, detected by the VLA. Then XMM-Newton detected the peak of the afterglow. You see the emission from the host galaxy, and here the emission from the afterglow after almost 150 days, 150 days after. And this is the overall afterglow, late time afterglow in the radio, in the X-rays. You see, we missed the initial part, and we have these late onset. And this is very nice. You see a collection of short gamma ray bursts, X-ray afterglow light curves on axis, you see. These are the limits from Swift for the X-ray afterglow 170817, and this is the late onset. If you take this and you back extrapolate, you match the on-axis, exactly as I was telling you before. And then the final stuff, because there were doubts if this was an off-axis, a slightly wide angle emitting GRB, thanks to the very late time, 250 days radio observation with a very high angular resolution, it was possible to understand that this was the model. A kind of jet with a structure observed slightly off axis, 20 degrees off axis, more or less. And this was because with the VLA, it was not possible to resolve the source with a very down to milliarc second. So not an isotropic emission, not an homogeneous jet, but a scenario like this. And you see, then it is a late, but this is. The final stuff I wanted to tell you is that, and then I conclude, is that after this big, exciting event, that we had other runs of gravitational wave, of the gravitational wave interferometers, but unfortunately, we are missing another multi-messenger event. There will be. This is interesting because these were the expectations for the 04 run we are living now about the possible detection of binary neutron star. You see, we were expected to detect almost 10 or more than 10 minus 10, so also consistent with 0. And yet we had a couple of detections with the so wide localization, basically your sky, that it was not possible to actually search for any counterpart. But what is there is that unfortunately we are having much less binary neutron stars than expected, while we have a lot of binary black holes detection with fantastic for physics, but not very interesting for multi-messenger astrophysics. Okay, stop here. I think, and then if you have any questions from a remote or in presence, you are welcome to. There will be also time at the end for the discussion session. So. I'm pretty sure that after a lot of talks, we will have a more complete view. Let's see if someone raised the hand. Okay, yes, Martin.
Hey, ciao. Can you hear me?
Yes.
Oh, okay, great. You skipped that, but I would ask about magnetars. Like, what would be according to you, the observational like signs or signatures for a magnetar emission? Like, if you don't count the gravitation wave moving down, which is the music of future. But,
I think I have 1 minute to answer this, Giancarlo, maybe. Okay, thanks. Thanks, Martin, for the question. Yes, I skipped it because not to run too much out of time. So then Maria Grazia is our expert here in magnetars, so she can comment and also later a discussion session. But in short, I told you that mainly thanks to the prompt repointing of Swift, we could collect a lot of information of the diversity and variety of the afterglow light curve shape, let's say, characteristic. And some of them are not that easy to explain, and so a magnetar powering progenitor has been invoked. For example, here in this sketch, you see here, I hope is orange, I'm a bit colorblind, sorry. So there is the prompt emission that can be multi-peaked, and then you have here, sticked here, the afterglow. So this is a typical canonical afterlight curve with a steep decay. That is a kind of the tail of the prompt emission, and then in many cases you see a plateau in the afterglow light curve, mainly in the X-rays. So why the afterglow can be energized at this point? This happens typically as 10,000 seconds after the T0, so a couple of hours. What can be there at play so that to slow the decay, almost powering something, and then the decay starts again. A possibility to explain this, because the decay is simple, it's fading, it's decay. But why this plateau? Possibility is that if the central engine is not a black hole but a magnetar, then invoking the spin down luminosity of the magnetar, that at some point you have an energy reservoir that can explain this. And then if you fit these with typical neutron star parameters, you end up that the spin down should be originated by a millisecond speed magnetar with a magnetic field of 10 to the 15 Gauss. So everything, but of course this is highly model dependent. And also the effect of the multiple flares at early times, that is the possibility of a magnetar has been invoked, taking from the X-ray binaries models the idea of the idea of the propeller. You have material accreting, and then because of the magnetic pressure, then you can halt the accretion, and then the accretion overcomes again, and so you can have this stop and go, turning on and off, providing the accretion, providing, for example, this sequence of flares. These are observational features. They are there, no doubt, in some of the GRBs, light curves. There is no univoque explanation of those. They can fit rather well invoking a magnetar central engine. But as I said before, the fantastic smoking gun would be to have residual, let's say, gravitational wave emission after the ring down. More difficult to find an alternative explanation. I hope Martin, this provide you the answer.
Thank you very much.